Jnanam paramam dhyayam. Knowledge is supreme.
Welcome to this course on advanced transition metal organometallic chemistry. We have been discussing a very important compound or class of compound in this context, and these are bis arene transition metal heteroleptic complexes. And in this regard, we have been talking about transition metal arene cyclopentadienyl complexes. These compounds can be thought about as a hybrid of bis cyclopentadienyl complexes or bis benzene transition metal complexes, so that the transition metal is bound to both of these ligand, that is the arene in eta 6 fashion and cyclopentadienyl ligand in eta 5 fashion. So, this makes this class of compounds very interesting. Now, in the previous lecture we have started off by talking about the synthesis of these compounds, and the method that we have used involved reaction of metal halides with cyclopentadienyl sodium salt and phenyl magnesium bromide Grignard, resulting in the formation of this manganese cyclopentadienyl benzene complex. But one of the characteristic feature of this synthesis is that the desired product, which is cyclopentadienyl magnesium benzene complex, was formed only in 2% yield. There were a mixture of other combination of products which were obtained, but the desired product in this method was very less in amount. Now, proceeding further, today we are going to take up some more synthesis of this mixed cyclopentadienyl metal arene complexes, and one such method involves ring expansion of benzene to cycloheptatienyl ring, as shown over here. This is a interesting reaction, as can be seen over here, that manganese is bound to two different rings. One is cyclopentadienyl ring and benzene ring. Now, treatment of this with RCOCl in presence of AlCl3 at minus 40 degrees centigrades leads to the expansion of the 6 membered ring to produce a 7 membered ring, as is shown over here. Now, the mechanism of this reaction is not clear, but what is evident is insertion of Rc plus into the 6 membered benzene ring. Now, this reaction also occurs with the chromium derivative C5 H5 chromium C6 H6, but does not proceed with free benzene or C6 H6 CrCO3. So, this reaction is kind of an interesting reaction in which cyclopentadienyl manganese benzene ring gets extended by treatment to a 7 membered ring by treatment with RCOCl with AlCl3 at minus 40 degree centigrade, resulting in Cp manganese 7 membered ring with substituted R cationic species. Now, the mechanism of this insertion, though not clear, but what is evident is that insertion of Rc plus cation into the 6 membered ring takes place, and this reaction is not only limited or restricted to this Cp manganese benzene compound, but can also be effectively used for another such complex, which is Cp chromium benzene compound, but cannot be used in case of free benzene or with benzene chromium tricarbonyl. So, this is an interesting reaction in which one can obtain the cyclopentadienyl methyl arene kind of complex. We are going to take a look at some more reactions to this effect. Another reaction involves just simple ring exchange. And this is seen in this beautiful example involving reaction of ferrocene plus arene in presence of AlCl3 and aluminum, followed by water workup, resulting in exchange of one of the Cp rings with the arene rings, giving this cationic iron complex plus C5 H6. And the notable feature is that only one ring can be exchanged and cannot be exchanged to bis arene complexes. So, only one of the cyclopentadienyl ring of this ferrocene complex can be exchanged in this ring exchange method. So, what we see so far that there is a wide variety of synthetic techniques that are available for preparing this mixed Cp arene complexes, and the first one obviously involved the simple reaction of taking metal halide with a source of Cp and the arene as a nucleophile. But the problem with that synthesis was that the yields were very low, despite that was probably the direct route of obtaining these compounds. The second method that we had seen involved the expansion of ring, 6 membered ring, and this we had seen by treatment of Cp manganese benzene with RCOCl and AlCl3 led to the expansion of the 6 membered ring to give this cationic Cp metal substituted 7 membered ring species. The third that we had reviewed involved ring exchange, in which the ferrocene was treated with an arene and one of the Cp rings were exchanged to give this cyclopentadienyl iron arene compounds. So, another involves the reduction of this cyclopentadienyl iron benzene compounds to form the corresponding 19 electron species, which as expected is a radical. So, Cp Fe hexamethyl benzene which is a cationic compound when reduced with sodium mercury in DME giving this is a 19 valence electron compound D6 giving the corresponding neutral 19 electron species. Valence electron D7 and this is a radical complex neutral So, this one particular one is a nice example in which one can obtain this 19 electron radical complex of cyclopentadienyl hexamethyl benzene iron via just simple reduction of another cyclopentadienyl hexamethyl benzene iron to cationic complex by using sodium amalgam in DME. Similarly, the reduction of nucleophiles lead to cyclohexadienol complexes. Similarly, the nucleophilic addition lead to addition of hydride lead to cyclohexadienol complexes. Now, this is interesting reaction in which the same complex Cp iron 2 hexamethyl benzene is a cationic complex is reacted with sodium borohydride and then the hydride goes and attacks at the ring giving rise to this neutral complex. The way it is shown here and which sort of illustrates that the addition of this hydride goes on to attack at this hexamethyl benzene ring. So far what we had seen that in case of the mixed cyclopentadienyl arene complexes, the ring expansion happened at the arene ring, whereas the nucleophilic addition occurred at the arene ring. Whereas simple reduction with sodium amalgam that only affected the metal center, which got reduced from +2 oxidation state to a +1 oxidation state in the previous example. So, for complexes like this, C5 H5 Fe paraxylene plus are suitable reagent for transfer of C5 H5 Fe plus unit under mild conditions. Here is another interesting example in which a ruthenium dimer was reacted with thallium Cp to form this mixed Cp ruthenium benzene complex, and this C6H5 ruthenium unit was transferred from its dimerate complex. So, we are going to see an example of along the same line C6H6 ruthenium unit transferring reaction. So, this is beautifully illustrated by this example of ruthenium benzene chlorodimer when treated with 2 thallium Cp in ethanol and 2 water NH4PF6, then 2 units of this desired Cp ruthenium benzene plus PF6 minus compound is formed. So, this is a interesting example where one can see this Cp ruthenium unit gets transferred from this dimeric complex by treatment with thallium Cp, resulting in the Cp ruthenium arene cationic complex of the type shown over here. Now, this ruthenium Cp units, these compounds ruthenium Cp benzene cationic compounds are photolabile and forms solvates. So, one interesting property of this is this C5 H5 Ru C6 H6 plus cations are photolabile and form solvates. that transfer for the C5H5 Ru plus unit. This is beautifully exemplified provided in the example given over here, where you have Cp ruthenium benzene plus in presence of H nu in acetonitrile, giving ruthenium Cn and complex, and that in presence of hexamethyl benzene C2H4Cl2 solvent at 80 degree centigrade gives the desired ruthenium benzene complex. So, one can see that these compounds can be used, particularly the Cp ruthenium benzene cationic compounds can be used as a source of Cp ruthenium cation unit transfer, and that is affected by a light in which the benzene ring falls apart, and then the vacant site is occupied by dative solvents like acetonitrile, and subsequently treatment of that solvated ruthenium Cp cationic species with arenes gives this ruthenium arene Cp cationic compound. So, this is an interesting example whereby one can make these mixed arene Cp metal complexes. Another example involves abstraction, successive elimination of two hydride ions lead to the formation of such kind of Cp metal arene complexes. So, this is another very interesting example that involves successive elimination of two hydride ions from a cyclohexadiene complex leading to the formation of the eta 5 C5 H5 M eta 6 C6 H6 species. So, this is beautifully shown in this cobalt compound. Cobalt the hydride abstraction is affected by triphenyl trityl cation, triphenyl carbon cation, which gives PH3CH, giving Cp, this is cobalt 1, cobalt 3, followed by second abstraction again by the same reagent, minus giving Cp cobalt 3. So, this after abstraction it becomes monocationic species, and after the second abstraction it becomes even dicationic species, and the desired cobalt 3 cyclopentadienyl benzene 6 complex. So, this is a interesting approach where hexadiene was converted to arene by abstraction of 2 of the hydrogens, ring hydrogens using trityl cation. Let me just reiterate that we had seen the reverse of it when just a few examples back, where we had seen that the arene complex when treated with sodium borohydride led to the formation of this hexadiene, where the hydride nucleophile attacked on the ring. So, just exactly opposite of what we have been talking about over here was discussed a couple of examples back, where the reduction ring reduction was carried out with sodium borohydride, and in the present case that hexadiene is converted by abstraction of the hydride with trityl cation to give the metal arene complex, and in the earlier example a metal arene moiety was converted to metal hexadiene complex by reduction with sodium borohydride, where the hydride attacked the metal bound arene ring. So, what we come across right now is just 2 opposing reaction which was discussed back to back into to show the type of versatility that one can get in these methods that we have been discussing. So, with that we would like to talk about conclude today's lecture, which had primarily been on various methods that are available for preparing these transition metal cyclopentadienyl arene complexes, and among the things that we have discussed, the one that stands out the most is that these compounds are probably the most versatile in terms of the synthesis is concerned, because we have discussed 7 different approaches that were involved in the preparation of this complex. To start with, we discussed the conventional approach, where one can start thinking about preparing this mixed ligand compound by taking the metal halide and the each of the ligand nucleophile, and then the problem of that method was that these were very low in yielding, and there were also side products. However, they could give rise to the desired mixed cyclopentadienyl benzene type of complexes. The next method in this today's discussion was the ring expansion method, where we saw that the a ring of a metal cyclopentadienyl benzene or arene ring was expanded from a 6-membered arene to a 7-membered arene by the treatment with RCOCl in presence of LCl3. So, this ring expansion method also is a very unusual method, in which a 6-membered metal bound ring was converted to a 7-membered metal bound ring, whereas the 5-membered metal bound ring remained intact. The third approach that we had spoken about involved the displacement of one of the cyclopentadienyl ring with another 6 membered benzene ring, and this example looked into the reaction of ferrocene with toluene reagent, in which one of the CP ring got discarded, replaced by another benzene ring. The next we discussed was just the formation of by reduction, the simple reduction, the formation of 19 electron species, in which cationic iron Cp benzene complex was treated with sodium mercury amalgam to make this 19 electron neutral iron Cp benzene compounds. We had also seen that the treatment of the same cationic iron Cp benzene ring with sodium borohydride led to the formation of this hexadiene bound iron cyclopentadienyl complex. We had also seen that the reaction of benzene ruthenium chloride dimer in presence of thallium Cp gave this mixed thallium Cp benzene, the ruthenium benzene compounds. And lastly, we had also seen two examples in which one can see the cyclopentadienyl ruthenium benzene cationic compound being photolabile and also form solvate can be used to make this mixed cyclopentadienyl benzene complexes. And last but not the least, we have also seen that if one can starts with a metal hexadiene Cp compound by suitable abstractions of the hydride, one can go to the target Cp benzene cobalt 3 dicationic compounds. So, what comes to the fore is the fact which I have already mentioned, that these compounds have quite a bit of versatility in terms of the synthetic methods that are available towards their synthesis. So, I am going to I have discussed about 6 or 7 of them in today's lecture, and going to continue further look further in the next next lecture and see why it makes these compounds so unique in terms of being the synthetic targets. We are going to also be looking at the reactivity and the structure and bonding and reactivity of these complexes in the next lecture. And so, I thank you for being with me in this lecture and also look forward to taking up this topic in bit more detail in next lecture, where we finish off with the synthesis and look into the structural reactivity of these cyclopentadienyl transition metal arene complexes. Till then, thank you and goodbye.